In this video, we're going to look at a few more definitions of quality factor. These are particularly handy when you're thinking about the behavior of individual components. And we like the idea of looking at the quality of individual components because real inductors and capacitors have some loss associated with them. For instance, inductors are usually made of loops of wire, which has resistance. It's also common to boost inductance by using ferromagnetic materials as inductor cores, and magnetization of materials has some energy loss associated with it. Capacitors have a similar behavior where polarization of the dielectric has a little bit of loss associated with it. In all of these cases, we model the loss on the component as a series resistor. For capacitors, this is commonly called the equivalent series resistance, or ESR. The main point of this slide is that ESR exists, but while we're talking about ESR, we can explain some puzzling design practices. In particular, you often see networks of bypass capacitors made of one big capacitor, like a microfarad, in parallel with a much smaller capacitor, like 10 nanofarads. If you were just looking at capacitance values, this design choice is puzzling. The smaller capacitor only changes your capacitance by about 1%, so why include it? However, if you think about ESR, the smaller capacitor can become significant. This is because big capacitance values tend to come with big ESR values, which means the impedance stops dropping with frequency and flattens out at a relatively low corner frequency as pictured in the diagram. You can think of this as the capacitor becoming a short circuit at high frequency such that the lossy capacitor starts looking just like a resistor. Adding another capacitor in parallel with a lower ESR can extend the effective bandwidth of your capacitor, like the green curve here. The overall impedance of the parallel combination will trace out the bottom of these two curves because the parallel operator is dominated by the smaller impedance. We quantify the losses in these lossy components by going back to the most fundamental definition of quality factor, which is 2 pi times the maximum energy stored in one cycle divided by the energy dissipated in one cycle. This definition means that a system that stores lots of energy without losing much will have a high quality factor. You might note that energy per cycle has units of power, and there are other definitions of Q that rewrite the denominator as an average power. I like this definition for a few reasons. First, it can help us remember the Q for series and parallel systems. In series RLC circuits, you get a high Q with a small r because current runs back and forth through the resistor every cycle, and a small value will reduce power dissipation. In parallel RLC circuits, you get a high Q with a big R because very little current will run in the resistor to be dissipated as it gets bigger. This reasoning can help you remember to put R in the numerator or denominator when calculating RLC tank quality factor values. Second, I find this definition aesthetically pleasing. It links the behavior of systems to fundamental physical quantities, and that's nice. Third, this definition is useful for defining component Qs, so let's do that. We're going to start by imagining that we have a capacitor in series with a resistor. The circuit is being driven by a current source with a 0 to peak voltage of with a 0 to peak value of IZP. We write down the standard equation for energy stored on a cap, but we run into a problem right away because we don't know the voltage on the capacitor. However, we can find it by multiplying the peak current by the impedance of the capacitor. We're skipping over some subtlety around the fact that the capacitor impedance is imaginary, but we'll circle back to that in greater detail later. Finding the power dissipated in a resistor is simpler. We find the average power by averaging I squared R over one cycle, and remembering that the average of cosine squared is 1/2. Then we multiply that by one period to find the energy dissipated in a cycle. Taking the ratio of these energies, and including the factor of 2 pi from our definition, we find a frequency-dependent value for the quality factor of capacitors. That frequency dependence makes some sense, because the peak capacitor voltage drops with frequency. Also, note that this quantity is the reactance divided by the resistance, which is a fast mnemonic for calculating component Q for series losses in either inductors or capacitors. The parallel version of this circuit behaves similarly. We drive it with a voltage source for ease of computation because the voltage will be the same across both branches. Our final definition of Q is the inverse of the series case, and the mnemonic for parallel circuits is that you take the ratio of susceptance to conductance to find Q instead of reactance to resistance. When you start mixing lossy components together, each of their losses contributes to the overall quality factor of your system. But the summing relationships for those losses depend on whether the components are added in series or parallel. I find it easiest to draw an equivalent circuit of the combined elements to calculate an overall Q, rather than remembering 4 separate relationships for series and parallel inductors and capacitors. We'll also see very soon that we can use a mathematical trick called a series to parallel transform to make calculating the Q of groups of lossy components easier. So, in summary, Q is defined by energy stored divided by energy dissipated. Components have an omega-dependent quality factor, which is given by the reactance over the resistance, or the susceptance over the admittance, or the susceptance over the conductance. And individual Q effects are combined in bigger circuits.